What happens when AI systems remember too much, cooperate too loosely, or drift just far enough from their rules? In this episode, we dive into three striking new ideas shaping safer AI: formal methods that audit LLM agents step by step, memory monitors that expose how long-term recall can quietly accumulate risk, and decentralized defenses that detect backdoors by listening to a system's neighbors. Together, they reveal a bigger story about trust, control, and the hidden failure modes inside modern AI. Let's explore the first paper: Formal Methods Meet LLMs Auditing, Monitoring, and Intervention for Compliance of Advanced AI Systems. This paper argues that AI governance needs product-level compliance monitoring, not just model-level safety. The core contribution is Track, a black box framework that audits and monitors advanced AI systems, especially LLM agents, against temporally extended constraints encoded in linear temporal logic, LTL. Instead of asking an LLM judge to reason over entire behavior logs, Track decomposes the problem into a labeling function L that extracts atomic propositions from each input-output step, and an LTL progression operator that symbolically updates the residual formula online, producing three-value verdicts and interpretable execution witnesses. In three environments, IPC trucks compiled from PDDL 3 preferences: Text World Cooking and Science World TRACR with even small LLM labelers outperformed direct LLM as a judge baselines on violation detection. The paper reports that small labeling models within Tracker matched or exceeded frontier judges, such as Gemini 2.5 Pro, while LLM judges degraded sharply as event distance, constraint count, and proposition count increased. The paper also introduces TRACP plus I, which adds predictive monitoring over a three-step horizon and black box interventions via best-of-n resampling, constraint-guided prompting, or safer model substitution. Across all tested model environment pairs, it reduced violation rates without significant task performance loss. The key novelty is the formal methods, LLM split. LLMs handle local semantic grounding, while LTL progression handles temporal correctness, yielding more reliable auditing and proactive control than prompting-only approaches. Let's explore the second paper: Remembering More, Risking More, Longitudinal Safety Risks in Memory-Equipped LLM Agents. This paper argues that the main safety problem in memory-equipped LLM agents is not a single bad retrieval, but longitudinal accumulation of retrievable content. The authors define this failure mode as temporal memory contamination and introduce a trigger probe protocol that evaluates fixed probe inputs against read-only memory snapshots built from stream prefixes, plus a null memory counterfactual baseline to isolate memory-induced violations from stream non-stationarity. Across three Office Assistant datasets, medical practice, university registrar, and persona-specific Enron mailboxes using 8 MEMEngine architectures, including full memory, short-term memory, long-term memory, generative agents, memory bank, self-controlled memory, MEMGPT, and MEMTree, memory-induced violation rates rise with exposure length, often reaching roughly 0.3, 0.5 on synthetic streams for broad retrieval, high summarization systems, while short-term memory remains around 0.1, 0.2. Order randomization shows the effect is driven primarily by accumulated content, not encounter order. The same pattern appears in claw-like agents on OpenClaw and SecLaw. Across 7 model platform configurations, violation rates increase from 0 to as high as 0.3 as memory grows to 20K tokens, and no system self-detects the unsafe behavior. A retrieval time monitor based on the event structure precondition trigger violation predicts these risks before generation, achieving 0.97 recall on medical and 0.984 on registrar, all performing domain rule baselines such as CI supervisor and CI checklist. The central design lesson is that broad semantic retrieval and aggressive summarization improve utility but measurably expand safety exposure over time. Let's explore the third paper: Your Neighbors Know Leveraging Local Neighborhoods for Backdoor Detection in Decentralized Learning. This paper addresses backdoor attacks in decentralized learning, where there is no server to inspect or filter poisoned updates. The proposed defense, Argus, makes each honest node reverse engineer candidate triggers from neighbor updates using a DE trigger style gradient optimization on a tiny local validation set, then cross-validates those recovered triggers with second hop neighbors using a top K energy map and structural similarity index measure, or SSIM. The key novelty is that false positive triggers caused by non-IID data are structurally inconsistent across nodes, while genuine backdoor triggers remain similar, so collaborative verification can reject malicious updates without knowing the trigger in advance. Argus also adds a trust state machine that moves neighbors from trusted to suspected after 2 consecutive rejections, and to ejected after 1 more rejection within the next 3 rounds. The paper is the first to give convergence guarantees for decentralized backdoor detection under asymmetric link failures, with a rate comparable to standard DPSGD and explicit dependence on the honest false positive probability PFP. On CFAR 1.0 with ResNet 8, Feminist with a 2-layer CNN, and Tiny ImageNet with ResNet 1.8, Argus cuts attack success rate from over 70% to below 7% on CFAR 1.0 and to near 0% on Feminist and Tiny ImageNet, while keeping clean accuracy within 5 percentage points of an omniscient oracle. Compared with Multicrum, BADFL, and P2PCD, its advantage grows as data heterogeneity increases. That's a wrap on today's AI paper highlights. Thanks for watching.